All right, you guys, today we're doing a little refresher on rotations by doing a composition, and we're also starting symmetry. So first I'm saying in example 1, perform the composition. So a composition is really a combination of 2 or more transformations. Okay, and then the transformations that we've learned about so far, all rigid transformations. We've learned about the translation, the reflection, and the rotation. So all of those are rigid transformations because they preserve the size and shape. We're just altering the place and position. So first up, I'm saying let's do a rotation 90 degrees clockwise about the origin. So that's really the only point that I've been having you guys rotate around is the origin. So right here will be our center of rotation. Okay, if we're saying clockwise, that means we're veering to the right. Okay, if you like to follow a rule, we know that that is saying X, Y, arrow to the right, Y, negative X. So what I like to think about when I look at my rule, it helps me just remember which direction it's veering in, which one takes the negative, means I'm pulling to the right. I'm rotating to the right. So I know that it's going to rotate into this position right here. Okay, I've taught you how to do it with the rule. I've also taught you how to do it without the rule, so it doesn't matter to me which way that you do it. Let's say that I do it with the rule this time. Let me transfer P, A, and W, those points on my paper. So P is at negative 3, 2. A is at negative 5, negative 2. And W is negative 2, negative 3. So if I apply the rule, right, it's telling me to switch the position for X and Y, and it's saying that all of those original X values are switching to the opposite sign. So if I switch here, first I'm going to take all those Y values and write them first. So 2, negative 2, negative 3. I'm going to take all of these X values and make them the opposite sign. So 3, 5, 2. All right, so I'm going to plot all of those new points. So I have 2, 3. So right here will be my new P, P prime. Okay, A will be at negative 2, 5. So right here will be my A prime. Okay, and then I need my new W, so negative 3, 2. So it's right here where the P is, same spot. I'm just going to put right here W prime. All right, so now I can connect my dots. My figure has rotated 90 degrees to the right with the clock around 0, 0, the origin as the center of rotation. All right, so there's my first step, right? I've done the 90-degree rotation clockwise around or about the origin. Okay, next I have to do the translation. So here in my rule, it's saying, okay, please translate 2 units left and 4 units up. So we're building off right here, all of the prime notation, all of those points, and we're going to slide it into its final position. So 2 left, 4 up. So let's say I start with the W prime. So 2 left and 4 up. So here's going to be my W double prime. Okay, for A, 2 left, 4 up. So here's A double prime. And then for P, 2 left, 4 up. Here's my P double prime. Okay, connect the dots. and then here is my final image. And I denote that with my double prime notation. So I'm showing here was my first stage, this is the rotation, and then we're sliding it into its final position here, which is 2 left, 4 up. All right, next we're looking at our different kinds of symmetry, and this is one of my favorite topics. So reflectional versus rotational symmetry. We see lots of things with symmetry in the real world. We see lots of things without symmetry in the real world. So first let's talk about reflectional symmetry. So if a figure has reflectional symmetry, that means that we can identify at least one axis of symmetry. So if you think of our faces and you draw a vertical segment right down the middle, right, that's a line of symmetry. Our faces have reflectional symmetry. So here again, let me define it. So a figure has at least one axis of symmetry. So I've given you a whole bunch of examples here. So first, my arrow to the right. If I'm looking for my line of symmetry, I should see that it's this nice horizontal pathway right here. Right, your line of symmetry is really a mirror line so that it can reflect over that mirror line and map onto itself. Okay, if I look at the heart has a vertical axis of symmetry, so right here. Okay, my little no sign, right? This could be like a no smoking sign, for example. We're saying no to whatever it is. I see 2 axes of symmetry. So whenever we see more than one, we say axes, and we spell it A-X-E-S. That is plural. So I see one here. So this would be a line of symmetry. Right, my figure would reflect over that axis of symmetry, that mirror line, and map onto itself. But I also see a second one, and it's right here. So here we should see exactly 2. If I had just drawn you a perfect circle, for example, a perfect circle would really have an infinite number of axes of symmetry. Okay, the last one right here, a regular pentagon. So any regular polygon will always have as many axes of symmetry as the number of sides. So if this figure is regular, that means that all the sides are congruent, so are all of the angles. So when I have an odd number of sides, I'm going to connect from a vertex to the middle of the opposing side, and that's going to be drawing in an axis of symmetry. So here I have my first one. Okay, I'm hopeful you guys can see that as a line of symmetry, an axis of symmetry. Okay, again, vertex to middle of the side opposite. Okay, here is a second axis of symmetry. Okay, vertex to the middle of the side opposite. Here is a third one. Okay, vertex, middle of the side opposite. Here is a fourth one. And then I have my fifth one, vertex, middle of the side opposite. And there is my fifth axis of symmetry. So remember what I said, I'm going to write it here. A regular polygon So again, regular means that all sides are congruent, so are all of the angles. We'll always have as many axes of symmetry So plural, it's with an E. As the number of sides. All right, so that's reflectional symmetry. We have to be able to identify at least one axis of symmetry. So one axis or more, it has reflectional symmetry. Okay, next we're looking at rotational symmetry. So if a figure has rotational symmetry, that means that it rotates onto itself at least 2 times within one full revolution. So one of my favorite examples is using a playing card. So here I use the 2 of clubs. Okay, but I'm going to pull a different playing card from my arsenal of playing cards. Let's say that I look at my 10 here. So here I have a 10 of spades. So this is another card that has rotational symmetry. So what I'm going to do is I'm going to picture right here, this is the center of the card right here. So if I rotate it 180 degrees, it should look exactly like itself. So here we go. Let me rotate 180. Does it look exactly like it did initially? It should. And then if I rotate another 180, it should be back to its original orientation. So we see that this figure has twofold rotational symmetry because it maps onto itself 2 times in one full revolution. So one revolution is 360 degrees. I could do the same thing with another playing card. I could do it with, say, the 5 of diamonds. I could also do it with, the 4 of clubs. Okay, the Queen of Hearts, another good example. And usually the backs of the playing cards, they design those to have reflectional, or I'm sorry, not reflectional, rotational symmetry as well. Okay, my deck of cards here is, I got gifted this. So this is Rio 2016 pack of cards, but it does still have rotational symmetry too. So here, if I put my pencil here, if I rotate 180, right, it does still look exactly the same as how it started, and then another 180, and it's back to its original orientation. Okay, so the backs of the playing cards usually, not always, also have rotational symmetry. All right, so first let me write that definition. So we're saying that it has rotational symmetry, right? A figure rotates onto itself at least 2 times within one full revolution. Okay, and then one full revolution is a full spin, 360 degrees. So if I look at my playing card, for example, so I have a little dot where the center is, right? Remember how I rotated it? So 180, usually draw arrows just to show how I'm rotating it, and then another 180, and it was back to its original orientation. Okay, if I look here, I have the same, like, no smoking type of sign, just like we saw over here. If I put my little dot here, I can picture how it could rotate 180 and then another 180. So both of these figures have twofold rotational symmetry because they map onto themselves 2 times in one full revolution. So for a regular pentagon, for example, here we're going to say that it has as many fold rotational symmetry as the number of sides. So if I put my little dot right here, and I picture it as like just cranking my wheel, right? I can rotate 1, 2, 3, 4, and 5 times in one full revolution. So let me add that here too. So a regular polygon. So regular, again, means that all the sides are congruent, all of the angles are congruent as well. So a regular polygon will have as many fold rotational symmetry as the number of sides. All right, so my playing card here, and the, no smoking sign, right? Here, these both have two-fold rotational symmetry. The regular pentagon has five-fold rotational symmetry. It also had 5 axes of symmetry when we're talking about reflectional symmetry. All right, so now I'm giving you 2 shapes, and I'm saying, does the figure have reflectional symmetry, rotational symmetry, both, or neither? And then explain. So if I'm looking at A, I'm looking at my regular hexagon. Well, this one, it's a regular hexagon, so it's a regular polygon. We know that we have 6 sides, so we have both. So if I look at my reflectional first, we would say that we have 6 axes of symmetry. So plural is with an E. So remember that we have as many axes of symmetry as the number of sides. So we have 6 sides when it's a regular hexagon. So when I draw them, I'm looking at vertex to opposing vertex because I have an even number of sides. So let me draw those in first. So vertex to opposing vertex. So we should see that that is a line of symmetry. Okay, here vertex to vertex. So another line of symmetry. Here is the last vertex to vertex. Okay, I also have to draw in the other 3 where I'm connecting the middle of a side to the middle of the side opposite. Let me show you that in a different color just so it doesn't get confused. So middle to middle of opposing sides. So here is 1, middle to middle. Okay, here is 2. And then here is the last one, that third one. So I had 3 that were vertex to vertex. I had 3 that were middle of side to middle of the side opposite. So I'm seeing 6 total axes of symmetry, which makes sense because I have 6 sides to my regular hexagon. All right, so then I want to talk about rotational symmetry because it also has rotational symmetry. And here we should have 6-fold rotational symmetry. So that's how we write it, 6-fold, because we can picture that here's the center. We're rotating once, twice, 3 times, 4 times, 5 times, and 6 times until it gets to its original orientation. If I want to express that as a degree measure, I take the 360, that's 1 full revolution, I split it 6 ways, and that gives me 60 degrees. So that's telling me that every crank, every time I rotate, I'm rotating every 60 degrees. So I'm going to write this as the figure rotates or maps overlapping with itself every 60 degrees. Okay, and then the second one, here I'm looking at, do I have reflectional symmetry, rotational symmetry, both, or neither? So if I try to find a line of symmetry, let's say that I use my ruler, right, that's not going to be a line of symmetry, right? It doesn't reflect over onto itself, right? That's what has to happen. If I try to find another one, would this work? I don't see that it's reflecting onto itself. Even if I try a diagonal, nope, it's not rotating onto itself. So here we would say it doesn't have reflectional, but does it have rotational? It does. So rotational, so right here, I can see how I could rotate my little yin-yang sign. Here, 180, here another 180, and it gets back to its original orientation. So this one would be rotational only. we would say twofold. Okay, how do I know what the degree measure is? Well, 360 divided by the twofold would get me 180 degrees. So my figure rotates, overlapping with itself or mapping onto itself. Every 180 degrees. All right, so there's our little intro to symmetry and a little review of compositions with a rotation and a translation. Have a good rest of your day.